Okay, so we're going to move now to two of the big theorems we'll be ending this semester with. And these are we're going to see how they relate to helping us find the flux through a curve or through a surface. So we're going to start first by recalling some notation. So recall we've seen this del operator before. This is this del operator. And we've seen it in the context of the gradient. When we applied it to a scalar function, we get this vector of partial derivatives. But we can generalize this notation, and we're going to define it such that this is an operator. And so instead of putting anything in the numerator, this is operator notation. I have the partial of, and I'm purposely leaving it blank here, and I'm purposely leaving what's in front of this as blank. So partial of blank with respect to y, partial of blank with respect to z. And if we write it like this, we can actually use this to help us do some shorthand notation for quantities that we're going to calculate a bunch in these last few sections. And so one of those quantities is what we define to be called the divergence of a vector field. And so first I'm just going to show you how to calculate it. And the shorthand notation we're going to use is to think of it as like a dot product. I'm saying dot product in quotes between this del operator, which is not really a vector, it's an operator, and this vector function. So if we were going to pretend like this del operator was a vector, and we were going to take the dot product, typically you would multiply the I components. But what we're going to interpret that as in terms of this operator notation is that we're going to apply the partial derivative with respect to x to this I component p. So we'll write this as partial of p with respect to x. And then just like a normal dot product, you're going to add what would happen if you applied this part of the operator, the partial with respect to y, to the j component. So partial of q with respect to y, and lastly partial of r with respect to z. So this is just shorthand notation for doing this mathematically, and we're using the del operator again because we notice we're taking some partials with respect to the different components. Okay, so for a physical interpretation, I really like this segment of the video done by 3 Blue 1 Brown. We saw a little bit of his video when we first introduced vector fields, and so I'm going to go back to his video, and he has a great YouTube channel with lots of great math videos as well as other interesting videos. Let's go watch a segment of it because I think he does a great job visualizing or helping us visualize what this divergence quantity actually means.
The ideas of divergence and curl are particularly viscerally understood when the vector field is thought of as representing fluid flow, even if the field you're looking at is really meant to describe something else, like an electric field. Here, take a look at this vector field and think of each vector as describing the velocity of a fluid at that point. Notice that when you do this, that fluid behaves in a very strange, non-physical way. Around some points, like these ones, the fluid seems to just spring into existence from nothingness, as if there's some kind of source there. Some other points act more like sinks, where the fluid seems to disappear into nothingness. The divergence of a vector field at a particular point of the plane tells you how much this imagined fluid tends to flow out of or into small regions near it. For example, the divergence of our vector field evaluated at all of those points that act like sources will give a positive number. And it doesn't just have to be that all of the fluid is flowing away from that point. The divergence would also be positive if it was just that the fluid coming into it from one direction was slower than the flow coming out of it in another direction, since that would still insinuate a certain spontaneous generation. Now on the flip side, if in a small region around a point there seems to be more fluid flowing into it than out of it, the divergence at that point would be a negative number. Remember, this vector field is really a function that takes in two-dimensional inputs and spits out two-dimensional outputs. The divergence of that vector field gives you a new function, one that takes in a single 2D point as its input, but its output depends on the behavior of the field in a small neighborhood around that point. In this way, it's analogous to a derivative, and that output is just a single number, measuring how much that point acts as a source or a sink. I'm purposefully delaying discussion of computations here. The understanding for what it represents is more important. Notice, this means that for an actual physical fluid, like water, rather than some imagined one used to illustrate an arbitrary vector field, then if that fluid is incompressible, the velocity vector field must have a divergence of 0 everywhere. That's an important constraint on what kinds of vector fields could solve real-world fluid flow problems. For the curl at a given point,
Okay, we're gonna stop it there. We are gonna get to curl in the next lesson, so have no fear. But for now, let's just focus on divergence. And right now, I've given you the formula of how to calculate it, and we just told you there's some physical intuition. We haven't proven why. And so at this point, if this is the point x naught, y naught, the divergence of the vector field at this point would be positive because I have like you could think of a gas expanding at that point or water coming out of a sink that's happening right here. And then here at this point, x naught, y naught, I would have negative divergence because you can think of a gas as like compressing or things were going in, oh, not a sink, a source. Sorry, over here, things are coming out of a source. That's what I was thinking. And in here, I'm thinking of them flowing down the drain of a sink. Okay. So let's actually just practice it algebraically. And so far, you should have no reason to believe that this is what it represents. We're going to get to that mathematically in a minute when we prove Green's theorem. But for now, I'm just going to have you practice calculating it. Let's go ahead and put this on pause and then see if you can calculate the divergence for each of these vector fields. Oh, okay, so here I'm going to just take the partial of this I component with respect to x, which will just be y, and then the partial of the q component with respect to y, which will just be z, and then the partial of the k component, or the k component here, which is just r. The partial of that with respect to z is going to be negative 2z, so this is going to be y minus z. And so notice here the divergence is varying depending on where you are in the vector field. Depending on what your x, y, and z values are, you will get different values for the actual divergence. Here, let's do this b vector field. The partial of the I component with respect to x is just 0, and the partial of the j component with respect to y is also 0. So this is called an incompressible field, like we saw in the video, because the divergence everywhere for any x and y is 0. And then lastly, we have generally the divergence of g here is just going to be partial of p with respect to x plus partial of q with respect to y. Okay, so now let's go and see exactly why this is giving us a physical interpretation of whether a point is acting like a source or a sink. And just to actually write out what I said, we define it to be incompressible if the divergence is 0 everywhere.